Hello, I'm here to inform you about the possibility of taking an online course in quantitative morphology built on stereological principles.
Here's a list of the lectures I'll be giving. Today we're going to start with the first lecture, the Introduction to Stereology. This is the first of a series of lectures designed to provide you with a basis for designing, carrying out, and critically evaluating quantitative studies of the structural features of biological tissues. Stereology is a method that allows one to make statements about total number, length, surface, and volume of the structural features in three-dimensional space. Those that are interested in using stereology in general have an area, structure, or tissue that they're interested in, and they want to make some statements about the organization of this tissue in quantitative terms. So generally we're talking about 3D objects or three-dimensional structures, and we're convinced that the internal structure defines the function and that we want to make some sort of quantitative statement about function based on the morphology or quantitative measures of the morphology. Now, the stereological method involves features or properties, and these are generally the goal of the study. We may be interested in the volume of a particular organ system, or the surface of that system, or the length of that system, or the number of objects within that system. Generally, you have to make sections through these three-dimensional opaque objects in order to see the structures that you're interested in. And when this happens, one loses one dimension, so volumes become areas and surfaces become lines, and linear features become cross-sections in a plane, and object number becomes difficult to understand relationship between the number of objects you see on the section and the number of objects that are actually within the volume you're interested in. So once again, stereology is a methodology that provides meaningful quantitative statements or descriptions of the geometry of three-dimensional structures from the measurements that are made in two-dimensional images. The principles of unbiased stereology are the following, and I'm going to go through them again after I have listed the basic components of a stereological analysis. For one, there is the interaction of unbiased probes with the structure, and we can have different types of probes such as point probes, line probes, area probes, and we can talk about the relationship between the interaction of the probes with the structural feature we're interested in. Here we're talking about the number of points that interact with the structural feature. Here the length of the line, and here the area of a section occupied by profiles of this. So what we can see from this is that there's an interaction here between the probes and the structural features. For example, when we look here at the surface feature, which appears as a line, we can use a linear feature and look at the number of intersections per surface area, or surface line, or the line that represents the surface. Here we could measure the length of the line and look at its relationship to the area. For length, we are limited to just using an aerial plane, as we look at here, in looking at the number of intersects per unit area. And when it comes to number, we'll talk some more about this, because it's such an important relationship, is that there is an inscrutable relationship between the number of profiles of an object and the total number of objects inside of a volume. and that one will have to use a two-dimensional probe in order to accomplish this. So in addition to having these probes that one is going to use for different parameters, one also has to be concerned about how one positions these probes within a structure. So what is being advocated here is systematic uniform random sampling of regions with probes. So here's a region of the brain, and this is showing the number or the placement of probes of different type to make estimates of the different structural features. And one thing that I will emphasize during the course is that when you do use the proper combination of probe and sampling scheme, you can produce estimates of total amounts that approach the true value as you increase the amount of sampling. This is the so-called definition of unbiased. For those of you who are not clear about this concept of unbiasedness, you can of course have experimental error at any one point that one makes a particular measurement, and this may vary to a certain degree, but on average we expect that it's going to end up giving us the true value. Whereas a bias technique will give a systematic shift away from the true value, and this cannot be reduced regardless of how much sampling one does. So what we really want to do here is get a sampling scheme or an estimation scheme that allows us to approach the true value as we increase the amount of sampling. Here we see the running average of means with increased sampling. Another way to look at this is to say that we can have a lot of precision in our estimation procedure, and on average it will give us the true value, and although the resulting values may vary considerably, on average they're going to give us the true value. This of course will not be the case with a biased estimation procedure, which will systematically deviate from the true value and can have different amounts of precision. The real issue here is that you don't know what the true value is unless you are using unbiased techniques. So this is what's very insidious. You don't see the bullseye when you're actually doing the analysis, and you're in this situation here. So the only way you can try to convince yourself or try to make the estimate as unbiased as possible is to use unbiased probes and unbiased sampling procedures. This is my point. Quantitative morphological studies that are going to be done with stereology, they're assumption-free. They can be called design-based stereology because we're going to design the probe and design the sampling scheme in such a way that we know that when we increase the amount of sampling, it will approach the true values. That is a very important aspect of the stereology we're talking about here. We're talking about a priori assumptions that are needed with other techniques that may in fact be wrong. So in this case we're talking about not having to know anything about the size, shape, orientation, or the distribution of the structural feature that we're interested in. Designed, therefore, is the key word here, meaning that we're going to design our study or our estimation procedure in such a way that it's unbiased. So here again is an indication of what is meant by unbiased estimation procedure. Here we have the true value. If we base this on then all of the sections within the structure we're interested in, then we only get one value. However, as we increase the distance between the sections that we may be using, and that is to say we start decreasing the number of sections. So in this case we've only used 6 sections opposed to 96 sections. Then we see that the variability that we get out of a sampling scheme with fewer numbers is actually related to the number of sections that are actually being used. As I said before, I'll come back to this point, quantifying geometry it is necessary to use geometrical probes selected for the parameter of interest. So here we have point probes, line probes, area probes, and a three-dimensional volumetric probe. And as I pointed out earlier, probes must be drawn uniformly from a tessellation of probes. This means that one would sample the structure of interest with a sampling scheme that permits all parts of the structure to have an equal probability of being sampled. So I'll repeat that again. We want a sampling scheme, uniform, and tessellation just means a pattern that's placed inside there. We want a pattern or a way to sample the tissue with the probes in such a way that all parts of the structure have an equal probability of being sampled. There are four types of probes: zero-dimensional points, one-dimensional lines, two-dimensional areas, and three-dimensional volumes defined by 2 points. So these all have certain characteristics. So what we're really interested in is the interaction between probes and features. So here we have a volumetric object here. It's been sliced. We see the profile of this object in 2 dimensions. We look at the number of points that hit the object versus the number of points in the test system. Here we look at the length of the line versus the total length of the line, and here we're looking at the area of the profile of the object versus the area of the section itself. And these measures can be used through mathematical relationship equations to relate to the volume of the object. For example, here the ratio of the red points to the total number of points here is going to be equal to the volume of the object versus the volume of the sample, or the reference volume. Here we're looking at the interaction of the line with the object versus the total length of the line, length per unit length, or area per unit area. All of these have the same relationship with the volume of the object per unit volume of tissue. So this is an integral part of the stereology, that is, the mathematical relationships which relate the interaction of the probes into the test system to three-dimensional value for that particular object. Now I hasten to add here that we have to be talking about the ratio, so this is the volume per unit volume, and I'll get back to how to use this ultimately to make estimates of total number. These are some of the origins of these relationship equations. They go back over 100 years, and you could say in a more rigorous way they relate the expected values of an unexpected probe set to the corresponding geometric value in 3D. So the math behind these relationships can be very complex and deep, but the relationships themselves are surprisingly simple. Here we see again going back to this VV versus AA all the way back to 1847. A lot of the early stereological techniques were developed by geologists to evaluate the amount of particular ore in samples that are going to be mined. There are other relationship equations besides those that I showed you up here for volume. They look a little bit more complex, but still are relatively simple in use. Here we can see that 2 times the number of intercepts per unit length is equal to the surface per unit volume, and 4 pi over the length of this line per unit area is also equal to the surface per unit volume. When we get down to length estimates, we have this very simple relationship. 2 times the number of cross sections per unit area on average will equal the length per unit volume. And notice that I say on average because statistical measure, and it has to be used in a particular sense. This is very similar to what one's doing with public opinion polls. So the goal of our study then is to obtain sample design produced unbiased estimates of total geometrical parameters. And this is because the group estimates can be compared, and these can be used in studies for development, aging, pathology, evolution, and so on. In the central nervous system, which I will be talking mostly about in the examples that I give, but are also applicable to other organ systems, we will focus on the number, the volume, and the length of particular estimates. Now we're interested in total geometrical parameters, so that means that the values that we get out of here are ratios: volume per unit volume, surface per unit volume, length per unit volume. And if we multiply that by the reference volume, that is to say the volume of the whole structure, then we can get at total volume, total surface, total length, and total number. Now the value of all of this is, of course, that one ends up with data that's intuitive, easy to understand. Here is an example of some data that has come from a study of the human entorhinal cortex and the number of cells in different layers. This data should be very familiar to most of them. Here you can see the mean number and for the group. In addition to that, we have an expression for variation in the group. And in a later lecture, I'll be talking to you about how much variability is there in each one of these estimates. That is to say, it is an estimation procedure, much like a public opinion poll, with a mean number and a margin of error, so you can actually characterize the accuracy of each one of these because of the type of data that we're collecting. This brings us to the point of talking about the design of a stereological study, and this is the choice of the probe and the sampling scheme. And this is perhaps the most difficult part of the stereological estimation procedure. We have to be concerned about the orientation and position of probes if we're talking about surfaces and lengths. We have to be concerned about how many individuals and how many sections and how many samples or probing do we have to do in each individual, remembering that if we're doing unbiased procedures, making no assumptions about the organization of the tissue, we can see that more sampling is going to result in more precision. So the issue then becomes, how much precision does one need? Or, comparable to a public opinion poll, what sort of margin of error is acceptable? And we're going to be talking about uniform sampling, or a type of systematic sampling, and I'll try to convince you in a later lecture that this is actually a more efficient way of sampling than just independent random sampling. So here's a diagram showing something about a sampling scheme. In the simplest case, we have a group that's going to be compared to another group. We have to consider how many of these do we need. In each individual, how many sections should we be using? And how many probes, let's say the dissected probe, do we need to place inside of here in order to obtain a satisfactory or acceptable amount of variation? We know that we can look at the individual variability if I were to repeat an estimate in the same individual, and I can see what that is. That's the mean individual variance. I can try to get an idea of that because I know the individual variability. This is the group variance. So if I know how much noise there is in making an estimate in an individual on average, then I can start determining whether the stereology sampling scheme that I have, I will know how much that contributes to the group variability. Because in the end, I might not be satisfied with the group variance. That is to say, the one that normally one applies statistics to in group comparisons. Unbiased stereology has a lot of power because the measures of unbiased estimates are unambiguous. When we know something about the total amount, the total length, the total number, total quantities, we can apply straightforward statistics. So here are some questions that you should ask yourself if you understand at this point before we go on to more rigorous discussions of the issues that I presented to you here.
I hope you enjoyed that and that you learned something new. We're going to move on now. As you can see, according to the program, it's going to look something like this. And later on, we're going to move on to different chapters. And you can get in contact with me at this address up here if you want to hear more about how you can get access to those other chapters. So thanks again for watching. I hope to see you again soon.